In this lesson, we're going to start talking about highs and lows of functions, of graphs, basically any way you can represent a function that we've talked about. And so by the end of this lesson, you should be able to answer the following little question. What is the first derivative specifically used for? And as a reminder, by the end of Unit 3, we're working on how do we make finding derivatives easier and what is the point of finding derivatives. So for the rest of this Unit 3, we'll be working on that big question 3 more so than number 2. All right, let's start with a warm-up. We'll draw the graph of a function with a horizontal tangent line. So maybe you draw something like that, and a horizontal tangent line would look something like this. Now, if we want to know the slope of this horizontal tangent line, any horizontal line has a slope of 0, so that slope would be 0. All right, so that was a quick little warm-up. Let's get to some definitions. So this lesson is going to be a little bit definition heavy because we're starting to take some of the ideas that we've learned algebraically and translate them to a graph. So we're going to need some more definitions. So we start with a local or relative maximum is a point whose y value is larger than any point's y values near to it, whereas a local or relative minimum is a point whose y value is smaller than any point's y values near to it. We also have the global or absolute maximum is the point whose y value is larger than any other point's y values on the graph. And finally, the global or absolute minimum is the point whose y value is smaller than any other point's y values on the graph. Okay, so that was a lot of definitions all at once, but basically we have two types of minimums and maximums. We have local or relative, same thing, but they go by different names, min and max, and we also have global mins and maxes. Okay, so to see the difference, let's identify the local mins and maxes and the global min and max of the function below. So if I'm looking for local, I'm looking for points so that points around it are smaller or bigger than that point. So for example, if I look at the point here and here, those 2 points, so maybe I call them A and B. A and B are local mins. And why are they local mins? Well, they're smaller than the other points around it. So when we're talking about local, we're talking about very small intervals around the point. So like if I were to look around that, I see every point around that is a little bit larger than A and B. Okay? If I want to think about local maximum, same idea. So this point here would be a local maximum. Maybe we call it C. So C, let me make my pen just a touch bigger. Yeah, okay. C is a local max. So now let's think about the absolute or global. So when we think about absolute or global maxes and mins, we want to consider the entire graph. So let's think about the absolute min first. So the lowest point on the entire graph actually is the same point that we called a local min. So B is also the absolute minimum because it's the smallest point on the entire graph. So B is the global min. And we don't have a global max. And why is that? Well, if I consider the fact that at negative infinity and positive infinity, my graph is going to infinity in both cases. So I don't have a biggest y value. So no biggest y value. Okay, so that's why we have no global max. All right, so hopefully that makes the definitions make just a touch more sense. But it is important to consider the visual aspect to these definitions as we go through the examples. All right, so now we're going to go into a little bit of theory. So we're going to talk about some more theorems. All right, so the first question that our theorems help us answer is how do we know that these extrema exist? And so extrema just means minimums and maximums all together. When we refer to them collectively, we just use the one word extrema. And this kind of gives rise to the name, the extreme value theorem. So the extreme value theorem gives conditions for a function to have an absolute maximum and an absolute minimum. So when you think of the extreme value theorem, what I want you to do is picture a cooked noodle. It's like a spaghetti noodle. And we define this theorem in two different ways. So mathematically, if a function f is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in a, b. Okay, great. We stated it mathematically. Now let's picture the noodle. So what this theorem is basically saying is if you have a spaghetti noodle and you bend it, then somewhere there has to be a maximum and somewhere there has to be a minimum. So no matter how you bend the noodle, you can always find a largest point and a smallest point on the noodle. Okay, so let's put that into words. So given a cooked noodle, no matter how you bend it, there will always be a max and a min. All right. So graphically, here's some examples of some graphs below that kind of demonstrate the extreme value theorem is true. So these are basically just some different ways to bend the noodle. All right, so I won't go through those explicitly, but take some time, look at them, think about which point on each graph is the max and which point on each graph is the absolute min. Okay. The next theorem we're going to briefly discuss answers the question, how do we know that horizontal tangent lines exist? So this one is called Rolle's theorem. And this theorem is actually very, very, very closely related to a theorem we've already learned called the mean value theorem, but you're gonna work on that connection in your extra practice at the end of this lesson. So Rolle's theorem says if a function f is continuous on the closed interval a to b, differentiable on the open interval a to b, and f of a is equal to f of b, then there exists an x value c in the open interval such that the derivative at c is 0. Okay, so if you remember MVT, you might be thinking that a lot of those conditions sound very similar. The ending looks a little different, but in the pre-recitation prep, what you're going to do is figure out that actually this is a special case of MVT. So we kind of already know how it works. It's just the special case where the derivative is 0. Okay, so below what we have is again some graphical representations of this theorem. So basically if we have a curve that's, basically a cooked noodle again, it's continuous and differentiable, then there is going to be a place where the derivative is 0, meaning that we get a horizontal tangent line. All right. So some examples of horizontal tangent lines are given in these graphs below. All right, now the big question though is how do we find extrema? So we've done these nice little theorems. We've said that they tell us that we can find extrema because they exist, but we don't know how to find them yet. So finally, we're going to answer, how do we find extrema? So first of all, maybe you've been noticing some commonalities between tangent lines at all of the local maxes and mins we've seen so far. So let's go back and just recap. The extreme value theorem said that we had maxes and mins. It didn't say that we had a derivative of any kind. Whereas Rolle's theorem specifically talked about the derivative and not maxes and mins, okay? So what's interesting though is if you look at these pictures of Rolle's theorem, you might notice that these horizontal tangent lines always occur at a max or a min, okay? So that's kind of what I'm noticing. So horizontal tangent lines occur at local maxes and mins. Okay, so that's an observation. So this next theorem is like crazy cool. All right, so this is called Fermat's theorem. I'm even going to highlight it because it's so cool. So what's so cool about this is if a function f has a local max or min at c and the derivative at c exists, then the derivative at c is 0. Okay, so let's unpack this because it's a pretty short theorem. So let's really unpack this and see what this is saying. Okay, so we had the first theorem, we had the EVT, which talks about maxes and mins. It should be ES. Okay, maxes and mins. Totally ruining my climax of my point here. Oh, come on, pen. Okay, maxes and mins. All right, we had our second theorem, which was Rolle's theorem, which specifically talked about horizontal tangent lines. And the amazing thing about Fermat's theorem, so Fermat was like a super smart mathematician, by the way. He did a lot of cool stuff. But what he did with this theorem is he said, hey, we've got these maxes and mins over here with the EVT, and we've got like the horizontal tangent lines with Rolle's theorem, and actually they're the same thing. So Fermat's theorem actually let us take the geometric idea of a max and a min and the algebraic idea of finding a horizontal tangent line, or like taking a derivative and saying that it's 0, and he kind of mashed them together. He said actually they're the same thing. So Fermat is kind of the reason why we can algebraically solve for maxes and mins. So that's pretty cool. So to do that, we need what's called critical numbers. All right, so sorry to get off the topic of Fermat's theorem really quickly. But again, that is a super cool theorem. So when you sit here and think about this diagram I drew for you right here, it's pretty wild. So without Fermat, we could not algebraically find maxes and mins. Pretty wild. I can't stress that enough. But we do need to talk about critical numbers. So we'll keep going with that. So we'll finally get into... Oh wait, I didn't mention what a critical number was. Okay, critical numbers are x values in the domain such that either the derivative is 0 or the derivative does not exist. So critical numbers are kind of like the first step to using Fermat's theorem to find maxes and mins. Okay, we're going to talk about what they are, but I think it's better to just jump into an example so you kind of get the idea from the context. All right, so let's dive into an example. We're going to find the relative and absolute extreme values, or extrema, it's the same thing, of f of x is equal to x cubed minus 3x squared plus 1 on the interval -1/2 to 4. So the first thing we're going to do is find the critical numbers of f in the interval a to b. So a critical number, remember, is f prime of c is equal to 0, or f prime of c does not exist. So either way, first thing we need to do is find the derivative, period. All right, so f prime of x If we take the derivative of x cubed, we get 3x squared. Take the derivative of negative 3x squared, we get negative 6x. And the derivative of 1 just is 0, so our derivative is 3x squared minus 6x. So the first thing I'm going to think about is there anywhere this derivative does not exist? Well, we don't have a fraction, we don't have a square root, so our domain of this derivative is all real numbers, so no, there's nowhere it doesn't exist, but we can set it equal to 0 and figure out what x values make it 0. Okay, so all of our critical numbers here are going to be where it equals 0. So solving a quadratic equation, we can actually factor this one. So I'm going to factor out an x, or actually a 3x. Let's factor out a 3x, and we're left with x minus 2. So x in this equation is equal to 0 and 2. So 0 and 2 are my critical numbers. Okay. Now we want to find the values of f at the critical numbers. Okay, so finding the values of f, so I'm going to take f of 0, and that's equal to 0 cubed minus 3 times 0 squared plus 1. And I'm going to find f of 2, which is 2 cubed minus 3 times 2 squared plus 1. So f of 0, well, we have 0 minus 0 plus 1. That's just 1. If we look at 2, that's 8 minus 3 times 4 is 12 plus 1. So we have negative 4 plus 1 is negative 3. Okay, so what we've done so far is we've found the local max and min, okay, or the relative. So, so far, we know that the relative max is the point 0, 1, and the relative min is 2, negative 3. All right, so at this point, once you've found the values of f at the critical numbers tell you local extrema. I should do that in red so that it's clearly a comment and not work. So critical numbers tell us local extrema. Okay, in the next lesson, we're going to actually learn that not all critical numbers tell us local extrema, but our local extrema must come from the critical numbers. Okay, so here we're going to take it for granted that because we got critical numbers, we get a relative max and a relative min, or local. So that's another way to say this. So just be aware when you're working minimum and maximum problems, they will use these words local, global, relative, and absolute extremely interchangeably. So be aware of all of them. Okay, so that's our relative max and relative min. And also notice that we write extrema as points. Okay, so it's very important that the maximum and minimum is not just an x value. If they ask for a maximum and minimum value, that can be a y value, but most of the time we're talking about x and y values together because we're talking about graphs, so we want to make sure we have points. All right, now we want to go on and see if we can find absolute extreme values, okay? So we had our local extrema already, but the thing is if we're finding absolute or global extreme values, then we also need to consider the endpoints of the intervals. So remember that very first graph we had here. And we had these points where the graph just goes off to infinity. So we don't actually have an absolute maximum on that graph. Well, if we restrict the graph to an interval like we do here, -1/2 to 4, then we can always have an absolute max or min on the graph, and that comes from the EVT. Okay, so we're going to find values of f at the endpoints a and b. So we're going to find f of -1/2, and we're going to find f of 4. Okay, so f of -1/2 is -1/2 cubed plus 3 times -1/2 squared plus 1. F of 4 is going to be 4 cubed plus 3 times 4 squared plus 1. So for this first one, we have -1/8 plus, or actually, yeah, plus 3 over 4 plus 1. So that's going to be -1/8 plus 6 over 8 plus 8 over 8. So what does that give us? 14 minus 1. So that gives us 13 over 8. And in the case of 4, we have 64 plus 3 times 16 is 48 plus 1. So that should give us 113. Okay, so let's parse out what this is saying to us. So we found on the entire graph, so I should also make a comment of this. So for this part, the interval was not considered. So we can find local maxes and mins on the entire graph. But when we go to absolute, we want to make sure we consider that interval. So we notice here that the 113 is a lot larger than that initial local maximum that we got. So our absolute maximum is going to be, so absolute max is 4,113, because that's even larger than the initial maximum that we got. So remember, for absolute, we're looking for the biggest thing possible on the graph. Now, for our absolute minimum, let's think about our absolute minimum. Our absolute minimum is going to be the point with the lowest y value, okay? So notice the two y values that we got here and here, well, they're both positive, but one of our local mins actually did have a smaller y value, and that was 2, -3. So the absolute minimum in this case is 2, -3. So notice we do have the case where you can have a local min or max also be an absolute min or max, okay? That is possible. And that is the end of that example. Okay, so a lot was going on in that example, so make sure if you have questions, make sure and ask. All right, one final example. I've been looking forward to this one. So this was actually Dr. Lanius's idea to put all of our pets into a word problem. So this should be pretty fun. All right, so Johnny, Chance, Manny, and Mocha are meeting for a doggy play date at a dog park. However, they can't all play together because Johnny and Chance are too big for Manny and Mocha. Furthermore, Doomstalker, a cat, doesn't care to play with any of the dogs. So, if the dog park is shaped like a rectangle, subdivided as shown into 3 yards to accommodate the different pets, and it was constructed using 3,000 feet of fencing, what is the maximum possible total area the pets have to play in? All right, so we have our picture of our dog park right here with all the little doggies in it and the one cat. So the first thing we want to do, so this is what we call an optimization problem. So optimization. And all this means is it's a word problem that deals with finding a max or a min. All right. The deal is you need to figure out what the function is that you need to maximize or minimize. Okay. That's kind of tricky because you're getting it from a scenario. But if you can do that, it's not too bad. So the first thing I'm looking at is the fact that it says 3,000 feet of fencing, and it also says maximum possible total area. So this is telling me I have two functions that I need to look at. I need the area of the dog park, and I need the perimeter of the dog park. Okay, and the perimeter here is going to include interior fencing. Okay, so those are my two functions that I need. So the area of a rectangle is length times width. So maybe let's label our picture a bit. So we have our length is this length, our width is here. Doesn't really matter which dimension you pick to make L or W. Now what we want to notice is each of these individual fences in here is also a W, and this other side is also an L. All right, so that'll help us get our perimeter plus interior fencing, but our area is always going to be length times width. Okay, so let's see if we can write the formula for our perimeter plus interior fencing. So we know from the problem that 3,000 was the entire length of our fence, and that's going to be equal to all the sides of this dog park added together. So we have 2 L's, and we also have 4 W sides. So my perimeter plus the interior fencing is going to be 3,000 is equal to 2L plus 4W. All right. So let's see what we can do here. So my problem says maximum possible total area, which tells me that I'm maximizing the area function. All right, so the area function is going to be our main deal here, but that perimeter is going to come into play. So let's write our area down again. Actually, let me make sure I leave myself some room. So area is equal to length times width. So the issue with this function as it stands is that it has 2 variables, and we don't know how to deal with things like that. I mean, we know we have implicit differentiation, but in this case, that's not really going to help us because we don't know anything about the derivatives or the rates of the length and the width, and they're not changing anyway. So what we need to do is figure out how to get the area function in terms of one variable. And the way we can do that is using the perimeter equation. Okay? So the perimeter equation, I can solve for either L or W. So maybe I want to solve for W because why not? So if I subtract over the 2L, I'll get 3,000 minus 2L is equal to 4W. So I get 3,000 minus 2L over 4 is equal to W. And if we simplify that just a little bit, that's going to be 1,500 minus 1/2 L. Oh, wait, no, 750. My bad. 3,000 divided by 2 is 1,500. So we have 750 minus 1/2 L. Okay, so now that I've found this, I can take this and plug it in for W. Okay, so now I'll have a function A of L is equal to L times the expression for W, which is 750 minus 1/2 L. All right. And now I have a function in terms of one variable. So I know how to take the derivative of this. Now my suggestion would be go through and distribute the L before taking the derivative. So we get A of L is equal to 750L minus 1/2 L squared. And now we just have a super nice polynomial that we can take the derivative of. So A prime of L is equal to 750 minus 2 times 1/2 is 1, so we just have 750 minus L.